Very well. Now, in the beginning of the concept of linear and time invariant systems, I said that a linear and time invariant system is clearly identified by its impulse response. However, we have also seen that, especially in continuous time, the impulse signal by itself is problematic. It's not physically realizable. You cannot make an impulse, and you cannot apply it as an input to a black box to see or to measure the impulse response. So how are you going to measure the impulse response of a continuous time physical system? How will you make a physical experiment then? Okay, that's a very real-life engineering problem. Up until now, I have shown you the mathematical tools to find the output if this input is applied. But it requires the knowledge of impulse response, and you cannot directly measure the impulse response because you cannot apply an impulse to the system. So what are we going to do? Let's now become more practical engineers, and let's try to think of a way to solve this problem. How are we going to find the impulse response? For an RLC circuit, for example, you have a circuit and you have function generators as the inputs. So how are you going to find the impulse response? Well, hopefully you will be able to get a step as an input, and you can measure the step response. So this thing is more manageable. You can make quite a sharp step as the input and see the output, but will it help you to find the impulse response? From the step response, is it possible to find the impulse response? Let's start thinking in discrete time again because it's easier. Suppose that you have a system in discrete time and it's an LTI, linear and time invariant system, and the impulse response is known to be h of n, which you don't know, but you want to measure it. If we apply a unit step function to that, what will be the output? The output will be convolution of the two, right? It will be y of n will be h of n convolution u of n, which is the input x of n. And what is that convolution? K from minus infinity to infinity, h of k, u of n minus k. Is that okay? The convolution in discrete time. That's fine. Now, this u of n minus k clearly has some properties. First of all, it is either 1 or 0. When is it 0? When is it 1? It is 1 if n is greater than k, or k is less than n, less than or equal to. And if k is greater than n, then it becomes 0. Because u of minus 1, u of minus 2, etc., they are all zeros. So this thing is equal to 1 if k is less than or equal to n, and 0 if k is greater than n. Okay. How can we impose this condition on the running index? K from minus infinity to infinity, we say, but we don't need to say it like that. Do you agree that this is the same as writing k from minus infinity to n h of k? Do you agree with this? Because from minus infinity up to n, it means k is less than n, or less than or equal to n. And in that region, it is equal to 1. This u is equal to 1. So it is h of k times 1. If k is greater than n, it becomes 0, so I don't write them. I impose the summation or the running index like this. So this is an accumulation. Of h, the impulse response, from minus infinity up to n. It's an integral or the accumulator of h. And this is the step response. And the step response I wrote as y previously, but it has a specific name, and we call it s of n. The step response is equal to the integral or the accumulated version of the impulse response. So the relation between the step response and the impulse response is this equation. Now this equation, the way that it represents the step response in terms of the impulse response is easy to understand. But the reverse, it's also easy. It's not very difficult, but it's a secondary operation because that's what we are looking for. We want to measure the impulse response. We observe this. We make this observation. So what is the impulse response is the question, which requires like an inverse system sort of thing. What was the inverse of an accumulator or an integrator? The inverse of an integrator is the differentiator or the derivative. In discrete time it was difference. So this is the inverse system. H of n is equal to S of n minus S of n minus 1. Do you remember that? We did this example before. So that's how you find the impulse response, just by observing the step response. This S of n is the step response. You make an observation, you plot, or you gather the information, you make the measurement, and find S of n. Subtract S of n minus 1, which is a right-shifted version of it. From that, the difference will correspond to the impulse response. And that's how you obtain the impulse response, without an impulse in the input. In the input, you use a step. Now, from here, the rest is just an extension. What is the unit step response in terms of the impulse response in continuous time? From minus infinity to t, h of tau d tau, which is the convolution of h of t by u of t in continuous time. H of tau times 1. So that is h of tau d tau. This is an accumulation or the integration of h, in other words. It's like the first equation here. This is analogous to this one. So from here, the inverse of the integral is the derivative, as we all know. H of t is therefore d by dt s of t. Simple. You take the time derivative, and these two are analogous to each other. I mean, they correspond to discrete time and continuous time counterparts. Clearly, in continuous time, this is more critical, because in discrete time, you can always apply an impulse in the input and see what is the impulse response. That is not a difficult experiment. But in continuous time, since you don't have an impulse, you cannot apply an impulse. All you can do is you can apply a step. And when you apply a step, what you will get will not be h of t. It will be s of t. This one. And from that s of t, in order to evaluate the impulse response, you need to take the derivative, the time derivative. The time derivative will correspond to the impulse response. Okay, let me ask you a simple example question. Suppose that you have an identity system. An identity system means that the output is the same as the input. Okay, so let's do it. Example: an identity system. So y of t is equal to x of t. Clearly, an identity system is a linear and time invariant system. And what is the impulse response, by the way? It's obvious. I mean, the answer is trivial. What is the impulse response? The output is the same as the input. So what is the impulse response? What? Impulse again. The input is the impulse, the output is the same. So the output is the impulse again. H of t is delta t, in other words. The impulse response is the impulse. But let's assume that we are not doing it that way. Instead, we apply a unit step at the input. So input is u of t, and output is the step response, s of t, is equal to what? Since it's the same as the input, it is also u of t. The step response is step, the same step. So what are we going to say as h of t? What is the impulse response then? The impulse response is the time derivative of the step response. Step response is, so it's the time derivative of s of t, and that is the time derivative of u of t. And by definition, it's delta t, which is the impulse. So the impulse response is now delta t. The example may be too simple, and it may even be confusing because of that. But all you need to know is this: if you have a step response, you have to take the derivative to find the impulse response. As simple as that. And in discrete time, the derivative corresponds to the difference, the top equation. Okay. This is more, the unit step response and such things are more commonly used in physical control systems and in physical systems as well. So it's important that you will be able to come up with a solution in real life. Now, we will try to conclude the linear and time invariant system chapter with the realizations. The realizations in discrete time and in continuous time, they are a little bit different. We will start with the discrete time realizations. So the new topic is discrete time realization of, realization of discrete time systems using block diagrams. So this is the new title of interest. And what are the block diagrams? That's the first part we have to deal with. The block diagram contains a single block, and we will use a lot of those single blocks, which is quite simply a delay element. So let me first define a delay element like this. That's a D in a box. A delay element is like this. If the input is x of n, then the output is x of n minus 1. It is just delaying our input by 1, integer 1. Of course, the block diagrams will also have summations, combinations of two signals, etc. So the difference equations will need to be solved and implemented in the block diagrams. It's a good idea to start with some simple input-output difference equations. And remember that if you have a difference equation, then it will correspond to a linear and time invariant system. Look at the first difference equation, which corresponds to a linear and time invariant system. Y of n plus a times y of n minus 1 is equal to b times x of n. Now, you may think of it like this. Suppose that this is a causal system. What is a causal system? A causal system means that when you apply an impulse, the output will start to become non-zero after zero. Can you find the impulse response of this system? So it's a question in parentheses. Question. And do it for your exercise. Y of n plus 0.9 y of n minus 1 is equal to x of n. So A is equal to 0.9 and B is equal to 1. That's an example. And we say that the system is causal. The question is, what is the impulse response? Can you find it? Please work on it. Tomorrow, warn me about solving this and check your results. Are you able to solve it correctly? Tomorrow we will see. Okay? But until tomorrow, that question, what is h of n? What is the impulse response? You have to work on it by yourselves for this evening. So this is a big parenthesis. Let's keep it aside. Let's look at the top equation again and let's try to implement it. What is y of n plus 0.9 y of n minus 1 is equal to x of n. That's 0.9. Sorry about that. Right. Okay. So how are we going to implement this one using building blocks? First of all, an input must come into the picture, and the scaling is indicated by an intermediate arrow like this with some scaling factor on it. Let's put a b here, for example. So at the end of the arrow, it will be b times x of n, just like the right-hand side of the equation. Excuse me, I want to copy this to here, like this. Y of n is equal to b times x of n minus a times y of n minus 1. I want to isolate a single y of n. That will be the output, okay? So now that I have more space, the input will be scaled by b. The input is x of n. And it will be added with a version of the output, where the output is, of course, y of n. Now, how can we get a y of n minus 1? Because at the input, we must have y of n minus 1 somehow. How are we going to get y of n minus 1? Using that block that I have given you, with the delay, I'll take one signal from y of n and delay it, so the output of the delay will be y of n minus 1. It must be multiplied by minus a, so I will put a minus a here. The output, which is y of n minus 1 at the output of this block, is scaled by minus a and added to b times x of n, and that summation will give you y of n. So are you happy with this block diagram now? This is the methodology or the way to get y from x for this kind of an input-output difference equation system. This difference equation requires a feedback, as you see, and whenever in the difference equation, whenever you have y of n minus 1, y of n minus 2, y of n minus 3, etc., the past versions of the output, from the output you need to put extra difference, extra delay components. Let's make another example. Y of n plus a1 y of n minus 1 plus a2 y of n minus 2 is equal to b times x of n. Another difference equation. Now the order of the difference equation is increased. The first one, the top example, was first order difference equation, like the first order differential equation. This time we have second order difference equation. We not only have y of n minus 1, but we also have y of n minus 2 as well. So how are we going to implement it? From here, the way to proceed is to write y of n isolated, and at the right hand side we have b x of n minus a1 y of n minus 1 minus a2 y of n minus 2. Okay? The overall strategy is the same. We have an input x of n which is scaled by b, and it is added to something. In fact, not only one thing, it will be added with two things. At the output, we have y of n. How are we going to get y of n minus 1? By delaying it, of course. And now here, I have y of n minus 1. That y of n minus 1 must be scaled by minus a1, and then I must delay it again, because I also need y of n minus 2. Okay, and here what do we have? We have y of n minus 2. That y of n minus 2 is scaled by minus a2. Those things must be added all together, and the graphical way of adding them up is like this. First I add up the bottom things, and then accumulatedly I combine it to the top, and that combination will give you y of n. So this is a second order difference equation that we have. But the orders are determined by the amount of delays applied to the output. What happens if I apply a delayed version at the input? So a new question, y of n is equal to b0 x of n plus b1 x of n minus 1. Now as you see, this is a zeroth order difference equation, but the input is delayed. Well, it's even simpler to do it. You do it like this. You have an x of n at the input, and that x of n is then delayed to have x of n minus 1. At these two branches now I have x of n and x of n minus 1. The top branch is scaled by b0, the bottom branch is scaled by b1, and they are combined to produce y of n. Are you happy with this? Okay. Now let's try to mix these two. What would happen if the input is first order and the output is also first order? Like this. We will see a few examples. So the new example is this one. Okay, let me give you a minute. Meanwhile, I'll give you the example. Y of n plus a y of n minus 1 is equal to b0 x of n plus b1 x of n minus 1. Like this. So this is a first order at the input and first order at the output system. Now, the strategy that I will adopt for the way to attack this problem is as follows. First, I will say that this will construct a new input. And the name of that new input, I will say Z of n. First, let's produce a Z of n, which will be then the input to the first order system. Is that okay? So I'm going to do it like this. Look at the top figure over there. Just like that one, I'm going to make an x of n at the input and the delayed version of x of n. And x of n is multiplied by b0. X of n minus 1 is multiplied by b1. And they are combined to produce Z of n here. Now this thing, this Z of n, will be the input to this system to produce Y of n. And how did we do that? Let's look at the first example here. Okay, the output is here, and there is a feedback coming down with a delay and scaled by minus a. So let's do it like that. Now Z of n comes into our system, and it produces a Y of n at the output. Y of n is delayed to produce Y of n minus 1, and it is multiplied by minus a. Do you remember why it was minus? Because this yn plus a yn minus 1, that a yn minus 1 will go to the right hand side with a negative sign, therefore it's a minus a here, and it will be combined with the input. So this overall shape is the block diagram for the first order input and first order output system. Now the reason that we have a dedicated section inside this chapter for this thing starts at this point. One of the key points of engineering, well, engineering has two key points. The first and the major key point is to find a solution, of course. And we found a solution. This is our implementation. But the difference between a good engineer and a bad engineer is the good engineer is expected to solve it in a cheaper manner, more efficiently. Those efficiencies could be faster or smaller. Here, there is no fastness sort of thing. The speed is not important, but the amount of delay components, you have to pay for it. Every delay component, here we have two delay components. Each of them has a cost, 1 cent each. If you have two delay components, this will cost you like, I don't know, 10 cents, including everything. But if you have one delay component only, it will cost you 9 cents instead of 10. 1 cent will be saved. Can we do that? Can we implement the same thing using one delay component only? That is the puzzle part, and the solution is fixed. I mean, it's not a very complicated puzzle. But first, let me ask you whether you can think of a methodology to have exactly the same input-output relation using only one D block. Is it possible? And if yes, how? And of course, if I ask you, the answer is yes, you can do that. That's what we're going to do. So how? Probably what you mean is correct. But the methodological way to attack this problem is to interchange these two linear and time invariant systems. Do you remember that if you interchange the time invariant systems, the overall combined effect will not change? So we have a system here and another another system here. Those two systems can be interchanged. That's what I'm going to do. So, but it's impossible to see the overall combined thing without first writing it like this. Then interchange them. When we interchange them, we will have the same input, of course, but now I'm going to draw it like this, like here. This is the output with a delay. I don't know what this signal is, by the way. Okay, I don't have a name for that. It's not the output. It's just an intermediate different thing that appears when I interchange the orders. It's not Z, it's different signal. That different signal is delayed, scaled by -A, and fed into here. So the right-hand side block is now drawn at the left-hand side, and then I'll draw the left-hand side block at the right, which is like this. B0, B1, combined. Now I know that the output is Y of n, because that's the eventual output. I just interchange the places of these two. And as you see, whatever this signal is, let's give a name to that. X, Y, Z, V of n. Okay. Let's call it V of n. This delayed version at this point will be V of n minus 1. However, as you see, this point here will also be V of n minus 1. So they are the same signals. Because the top signal is the same, the bottom signal is the same. I'm using a delay element, one delay element to produce V of n minus 1 from Vn. And I use another delay element to produce V of n minus 1 from V of n. Now that is redundant. This portion is redundant. There is one Vn and I need to find only one Vn minus 1. So I combine those two delays. And I will only have one delay. To the left, it goes by multiplying with -A. And to the right, it goes by multiplying with B1. Here, it multiplies by B0. And the output is Y of n. Strangely, this simple thing with a single delay element only is equivalent to this top thing. Just by interchanging places, I share one delay component to perform a delay operation to an intermediate signal, and the output is both going to the left-hand side as a feedback and right-hand side as a feed forward. But they are the same. The bottom signal here is the same as both to the right and to the left. So I don't need two separate delay components. And the input is, of course, X of n. This is the critical thing. If you have a difference equation which requires delays in the input and a difference equation which requires delays at the output, the number of delays that can be shared is the engineering problem. For example, if it's a fifth order difference equation, so you have y of n minus 1, y of n minus 2, n minus 3, n minus 4, and n minus 5. Okay? And you also have x of n minus 1, x of n minus 2, x of n minus 3, x of n minus 4, and n minus 5. Those 5 delays can be shared in the middle. So instead of using 10 delay elements, you will use 5 delay elements. Let's quickly have an example. Y of n plus a1 y of n minus 1 plus a2 y of n minus 2 plus a3. I'm not going to draw a fifth order, I'm going to draw a third order. A3 y of n minus 3 is equal to b0 xn plus b1 xn minus 1 plus b2 xn minus 2 plus b3 xn minus 3. This is the input-output relation, the difference equation. First, I will consider this delayed components at the input side and construct a new input z from these x's. And how am I going to do that? This is x of n. This is the delayed version, which is x of n minus 1. And I'm going to use x of n minus 1 going to the right. This x of n itself will be multiplied by b0. X of n minus 1 will be multiplied by b1. Then delay it again to have x of n minus 2. X of n minus 2 will be multiplied by b2. And then I will have x of n minus 3, one further delay, multiplied by b3. And they will be combined. To produce an intermediate z of n. Now this intermediate z of n will be used as an input to the third order difference equation at the output side. And I will start by drawing y of n, because that's what I need, as it's the output. Then I will have y of n minus 1, y of n minus 2, etc. like this. This is y of n minus 1. Y of n minus 1 will be multiplied by minus a1 at the feedback. Then I will have y of n minus 2, which will be multiplied by minus a2, and then delay it again to produce y of n minus 3, which will be multiplied by minus a3. And then they will be added together to produce y of n. It's a little bit cumbersome to draw these things. It's taking a lot of time. But what I'm going to do is to interchange these two. And then when I interchange them, these will be side by side. So each pair in those side by side things will be combined to a single delay. So first I'm going to draw this portion at the left hand side, and then I'm going to draw the left hand side portion at the right hand side, and I will do that now. Are you trying to draw these things? Probably you will be able to find these illustrations in the book, but anyway, let me give you some time then. Meanwhile, the others may think of how to combine those delay pairs. Can I proceed now? Because the space for this drawing tablet is too limited. Well, anyway, I have to proceed. Now, the right-hand side I am going to draw here, which has an input. The input is x of n. But the output is something whose name we don't know, but that thing is delayed and scaled by minus a1, and then delayed again and scaled by minus a2, and then delayed again and scaled by minus a3, like this. So the right hand side of the top figure, which is gone now, is here. And then the left side was like this: delay scaled by the top is going to be scaled by b0. The delayed version will be scaled by b1, and then we are going to scale it again, and then scale by b2, and then delay again and scale by b3 and combined here. And the output is y of n. It's clear, right? Since the top signal here at this point and here at this point are the same, it's v of n. This point is v of n minus 1, and so is this point. This point is also v of n minus 1. This point is v of n minus 2. This point is v of n minus 2. So we have to combine the delay elements from top to bottom to a single one. Well, if I were drawing with on the board, I would just simply erase the intermediate, and instead of those two delays, I will put one. So in the central point, at least, what we are going to see is a delay going to the right and to the left, another delay going to the right and to the left, and another delay going to the right and to the left. So the central portion of this top figure should be substituted or replaced by this. So instead of 6 delay elements in the top, we can combine each pair and have only 3 delay elements in the central portions only, like this. So, yes. Yes, but it's the feedback portion. Look at the right hand side at the top here. Look at here. If the input, whatever that input is, the input is now x of n, but it was previously z of n, as you see. Whatever that input is, it goes to the right, and the output is delayed, and the feedback is scaled by minus a1. That's what it is. The output is delayed and scaled by minus a1. So the right hand side at the top is drawn here at the left hand side. It's that figure. And only then I'll be able to share the delays. Now I'm going to ask you 2 exercises for tomorrow. Try to draw these 2. What would happen in those cases? Because they are very confusing. One of them is this. Suppose that the exercise first question is y of n plus a1 y of n minus 1 plus a2 y of n minus 2 is equal to b0 x of n plus b1 x of n minus 1 plus b2 x of n minus 2 plus b3 x of n minus 3. So what is the difference between this question and the question that we solved? Yeah, the output has one less component. Try to draw it. So how many delay elements could be shared now? It was previously three of them were shared. Now 2 of them will be shared, 1 will be extra, but in the total we will need again 3 delay components. But these 3 and the overall simplified structure is different from the second case. Y of n plus a1 y of n minus 1 plus a2 y of n minus 2 plus a3 y of n minus 3 is equal to b0 x of n plus b1 x of n minus 1 plus b2 x of n minus 2. This time the input is missing one term. And the structures after the interchanging, how will they look like? Make sure that until tomorrow you are able to draw these two cases. These two cases are like the case which can be generalized as follows. The input has delays up to m, okay? So the delay up to m at the input, and the output has delay up to n. If m and n are equal, then they can be shared, perfectly matched. What would happen if m is, so we have the case for m is equal to n. This is okay, just interchange, that's fine. What would happen if m is greater than n? And what would happen is if m is less than n in general? How shall we share? At which points? Are we able to draw these things? And I bet that you will be confused. Okay? So please make sure that you are able to draw these things before the examination. Because this much is what I will show in the classroom. But of course, in the exam, I will ask some more complicated sharing issues. So are we able to solve those things? We will see. Okay? Now we can stop at this point. We'll continue tomorrow.